Good afternoon, everyone. Let's start. In the previous class, we looked at some conditions on necessary and sufficient conditions to design prefix-free codes, in particular necessary and sufficient conditions on the codeword lengths in order to obtain a zero-error prefix-free code. And we saw that for every prefix-free code, the codeword lengths must satisfy the following Crafts inequality, which says that the sum of 2 to the minus the codeword lengths should always be less than or equal to 1. All right, and also if you have a set of lengths or a set of positive integers which satisfies the Crafts inequality, then it is possible to design a prefix-free code with the corresponding lengths. And we use this idea in order to design a prefix-free code for given any PMF, right? So given any source with PMF P1 with probabilities P1, P2 up to PM, we can choose codeword lengths Li equal to the seal of log 1 over Pi to base 2. And this set of lengths, as we saw, satisfies Crafts inequality, which means that there is a way to design a prefix-free code with these lengths. And how do we design the corresponding code? Remember that we had the following tree representation. So you look at Lmax, draw the complete binary tree of depth up to Lmax, and then in a greedy fashion, you assign code words, right? So that gives us a way to, it might be a little complicated for large sources, but nevertheless, it is possible to design a prefix-free code, no matter what the complexity is, right? And what does the Shannon code guarantee? So with these lengths, we can construct a prefix-free code, and we have an upper bound on the expected length. So the expected length is guaranteed to be within 1 bit of the entropy. So expected length, expected L of x, which is summation I going from 1 to m pi li. This is going to be less than or equal to h of x plus 1. It could be much smaller than h of x plus 1, but in the worst case, it is going to be h of x plus 1 bits. So that seems to be good. So now in this class, we'll see an example and see what is the best that we can possibly hope for. Is there a lower bound on the expected length, on the minimum expected length for any prefix-free code? We'll see that there is indeed such a lower bound, and that turns out to be equal to the entropy. Okay, and then we'll have a short discussion about what happens if we do, instead of doing symbol-wise encoding, what happens if we do block-wise encoding, and so on. Okay, so that's to come. Any questions so far? Any questions? All right. So let's continue. So let's see a small example of designing the Shannon code. Okay. Let's take a small thing. So we'll choose the following PMF. Assume that the alphabet is, say, A, B, C, D. The alphabet has size 4. And let us assume that P of A is, say, 0.3. P, the probability of occurrence of B is 0.5. The probability of occurrence of C is 0.1. And the probability of occurrence of D is also 0.1. Okay, and this is a valid PMF, so it sums to 1. 0.3 plus 0.5 is 0.8 plus 0.2 is 1. All right. So now let's try to compute the Shannon code. All right. So what are the lengths? So L of A would be seal log 1 over P of A. Similarly for B, C, and so on. So if I look at the length vector, which is L of A, L of B, L of C, L of D, can you compute and tell me what these are going to be? Yes, anyone?
2144.
Okay, so Pranav says it's 2, 1, 4, and 4. So the length corresponding to A will be 2, for B it is going to be 1, for C it's 4, and D it is also going to be 4. Okay, so now let's design a prefix-free code with these lengths. We need to construct a binary tree of depth 4. All right, so let's order the lengths in increasing order. So 1, 2, 4, and 4. So this is for B, A, C, and D. All right, so you start from the root. You have to construct code word of length 1. So let's call this the first code word. This is for B. So for A, what is it going to be?
1 and 0.
1 0.
Okay, so 1 0. So that's right and then left. What about C?
1 1 0 0.
1 1 0 0.
So 1 1 0 0. So this is going to be for C. And so let's write down the code words as well. So for A, for B it is 0. For A it is 1 0. For C it is 1 1 0 0. What is it going to be for D?
1 1 0 1.
Exactly. So 1 1 0 and 1. So this is going to be D. 1 1 0 1. Okay, that's good. So these are the code word lengths. So remember that the probabilities were 0.3, 0.5, 0.1, 0.1, 0.5, 0.3, 0.1, 0.1, and the code words are 1, sorry, sure, 0.5, 0.3, 0.1, 0.1. This is for B, A, C, and D. And the code words are 0, 1, 0, 1, 1, 0, 0, and 1, 1, 0, 1. The lengths are 1, 2, 4, and 4. So what is the expected length for this in this case?
One 1.9.
1.9.
1.9, is it? Okay, so let's say that's 1.9 bits. What is the entropy?
1.685, sir.
Okay, 1.685. Okay, so the expected length is 1.9 bits, the entropy is 1.685 bits, so it's a little higher than the entropy. Okay, so good. Anyway, it's anyway guaranteed to be within 1 bit of the entropy. All right, so that's fine. So now you know that if I give you any source, that is the corresponding probabilities, you can construct the Shannon code for that particular source. Now, let's look at this code that we just designed a little more carefully. Do you think this is the best code that you can design for this code? Can you do better? Is it possible to assign shorter code word lengths for some symbols?
For C and D.
Exactly, for C and D, right? Because you're assigning code words of length 4 for C and D, but whereas in fact, if you look at the code word tree, you can immediately see that I could have assigned this code word for C and this code word for D, and in that case, the expected length would have been much smaller. So for A and B, the code word lengths are the same. For C and D, the code word lengths are shorter, and therefore this is strictly better than what we just designed, right? So if I did that, then the code word lengths would instead be 1, 2, 3, and 3. And what would the expected length be?
One 1.7.
1.7. Right, so this is definitely better than what we just designed. But then it's not always clear. Well, one may wonder, if I give you a general source, then how do we get the best possible code? And we'll see that, see how to design the best code. The Shannon code, although it is simple, and it's sort of a first step in designing a prefix-free code, it's, as we just saw, it is good, but not the best. Right? So what is the best code? What is the best that we can possibly hope for? All right, so we'll take a different route for this. We'll first try to get a lower bound on the expected length for any prefix-free code. Okay. Any questions?
Yeah, we could always start with the Shannon code and like take the maximum length and decrease it by 1 and check the Crafts inequality. If it holds, then that's good.
Okay,
And
so that's a strategy. That's definitely a strategy. You first start with something. You start with the Shannon code, and then see if it is possible to assign kind of shorter code word lengths. Right? That's the strategy. But okay, that may work. But how do you know if that is going to be the best? Right? It's certainly an approach. So that would be sort of the greedy approach, right? You first greedily construct a code and then try to trim it down, try to trim down some of the code words, and that may work. That may not work for an arbitrary source. In fact, we'll see a more systematic way of designing a code, one which is provably going to be the best code with the smallest expected length. Yeah. Any questions? Any other questions? All right, good. So before we go to the next sort of subtopic, let's have a short quiz, just to make sure that.
Sir,
Yes.
one thing. Here in the length,
Mhm.
the code length for B, A, C, and D, we take log of 1 by P and the seal function. So the actual lengths that we get is like in the order A, B, C, D is 1.71, then 3.32, like that we get.
Sorry, 1 point. Fine. So if you look at log 1 over Pi, you mean?
Yes, sir.
You get 1.7 and then
1.
1.
3.32.
3.32.
Yeah, same 3.32.
Fine.
So
Okay.
I'm just asking, instead of this the seal function,
Okay.
here when we in general when we try to see this approximation, we take like the between one. So like 1.7 is closer to 2 than
Okay.
to 1.
Okay.
If we use that logic, then we will get 2133, no sir.
True, true. So again, you can always tweak things a little bit. So you know that this should be approximately somewhere between 1 and 2. This is of course going to be 1. This has to be either 3 or 4. This has to be either 3 or 4, and you can try to check, right? So as long as you have some set of lengths which satisfies the Crafts inequality, it's going to work. Correct?
Yeah, okay.
But remember, maybe in a different case, this may be something like 3.49 or 3.49, and this may be say 1.7 or something of that sort. In which case, if you just round it off to the closest integer, it may not always satisfy Crafts inequality.
Okay, sir.
All right. So I agree. It'll work for many sources, so you can sort of try to. So the approach that you're suggesting, that both you and I think Pranav suggested, are these greedy approaches. So try to check. I mean, so Shannon's code is bad, so try to make some small adjustments to it so that it still satisfies Crafts inequality, but you get an expected length which is definitely smaller than what Shannon's code gives us. All right, so that's a valid approach. That's definitely an approach which one can try. But as we'll see later, there is a better approach. There is in fact uh, it resolves many of the issues with Shannon's code, and there are sort of two main issues. One, of course, as we just saw, it doesn't assign the best possible code word lengths. You can in fact choose smaller code word lengths. That is point number one. Point number two is that even given the code word lengths, this sort of approach it's a greedy approach, and 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 ideally we want an approach which is more systematic, where you can sort of design an algorithm which works more efficiently. And we'll see that we'll have a recursive construction which is basically Huffman codes, and that resolves both of these issues. It gives you the best possible expected length, and the construction is also fairly simple. Okay. So we'll see that the Huffman code is indeed optimal in many senses. So there's no real need to try to improve the Shannon code per se. Right? Any questions? All right. So let's have a quick quiz. I will assign the quiz now. Yes. So I have assigned it on Google Classroom. I will also post the link here in the chat box. Yep, you should have access to it. You can take maybe 3 or 4 minutes to solve it. It's pretty simple. I can take maybe 1 more minute. Has everybody submitted? Anyone yet to submit? Okay, so I'll assume that everyone has submitted, and I'll stop accepting responses. Right, so there were two questions. One was you were given a particular code and you were asked to identify what kind of a code it is. So the code, it had code words 0001, 101, and 111. The code words were 0001, 101, and 111. This is clearly a prefix-free code, so no code word is a prefix of any other code word. So it is prefix-free, which implies that this is also uniquely decodable and therefore also non-singular. Right, so it satisfies all of these three properties. And in the second question, is it possible to construct a prefix-free code with the code word lengths 2, 3, and 3? Yes, it is possible because this set of code word lengths satisfies Craft's inequality. So the Craft sum is 1 over 2 square plus 1 over 2 cube plus 1 over 2 cube, which is a half strictly less than 1. So it is possible to construct. All right. Okay, so let us proceed. Now we just designed a code, the Shannon code, which achieves an expected length of h of x plus 1 bits, right? Of something less than or equal to h of x plus 1 bits. But what is the minimum expected length that we can achieve using the best possible prefix-free code? Right. So let's look at this particular problem. We want to find what is the minimum over all prefix codes of the expected length. Right, so this is what we want to find out. Let us call this L star. Right. Now we know that every prefix-free code must satisfy Craft's inequality. Right. So this is basically what is the expected length equal to. So it is a summation I equal to 1 to m pi li, and we know that the pi's are given to us, of course, and our goal is to design the li's. So one can pose this as a problem of identifying integers L1, L2 up to Lm such that these correspond to a prefix-free code. right? Or equivalently, since we know that there's a one-to-one correspondence between the lengths of a prefix-free code and maybe not. We know that every prefix-free code must necessarily satisfy Kraft's inequality, less than or equal to 1. Finding the minimum expected length essentially corresponds to solving this particular optimization problem. It's a constrained optimization problem where you minimize the expected length, which is summation overall I pi li, and the minimization is overall possible L1, L2 up to Lm, which of course have to be positive integers, and they should satisfy Kraft's inequality. Right? So one can sort of try to solve this particular optimization problem and try to at least obtain a lower bound on this particular quantity. So if you try to do that using maybe Lagrange multipliers, you'll get that this is always going to be greater than or equal to h of x. Okay, you can try to solve the optimization problem per se, separately, but there's a different approach, a more information theoretic approach of showing that the expected length is always greater than or equal to the entropy, right? And that's what we want, right? We want simpler proofs of difficult statements. So the claim is that for any prefix-free code, we have the expected length is always going to be greater than or equal to the entropy. No matter how you design the code, no matter what the complexity of designing the code or encoding or decoding is, the minimum expected length is always going to be greater than or equal to the entropy. Okay, and this is what we want to prove. Okay, so let us look at the quantity on the left-hand side. So this is summation I equal to 1 to m pi li, and let us take this minus the entropy. Okay, we'll start with expectation of L of x minus the entropy. So all we have to show is that this quantity, this difference, is always greater than or equal to 0. So we have summation pi li, which is expectation L of x, and the entropy, as we know, is summation pi log 1 over pi. Okay. Now I'm going to rewrite li in the following manner. I'll write this as pi log. So li is also equal to log 2 to the li. All right. So this is the same thing. I've just written li as log 2 to the li, but I'll write it in a slightly different way. I don't want to write it as 2 to the li. I want to write it as 1 divided by 2 to the minus li. Okay, and this minus summation I equal to 1 to m pi log 1 over pi. Okay, so let's combine these two summations. I equal to 1 to m pi log, well, it's minus pi log 1 over pi, which is plus pi log pi divided by 2 to the minus li. All right. So does this quantity look familiar to you?
The kale divergence.
Yeah, it looks like a KL divergence. It's not exactly a KL divergence because the 2 to the minus li's may or may not form, may not sum to 1. So it's not necessarily a probability distribution. But we know that since it's a prefix-free code, summation I equal to 1 to m, 2 to the minus li is definitely less than or equal to 1. And 2 to the minus li is anyway greater than or equal to 0, right? So it's strictly positive. Okay, so we have this. But now what I can do is I can use the log sum inequality. And what does the log sum inequality say? So summation ai log ai by bi is always going to be greater than or equal to summation ai, which is summation bi log of summation ai m pi divided by summation bi. Right, so this is just an application of the log sum inequality, and it holds for any set of positive numbers. Right, so all the pi's and all the pi's are anyway greater than or equal to 0. Strictly, we'll assume that all the pi's are strictly greater than 0, and anyway 2 to the minus li is strictly positive. Right, so what is this equal to? It is 1 into log summation pi is 1 divided by summation I equal to 1 to m 2 to the minus li. So what can you say about this quantity? You know that summation I equal to 1 to m 2 to the minus li is less than or equal to 1 since the code is a prefix-free code, right? So this is prefix-free and Kraft's inequality, right? So what can you say about log 1 over
Positive.
summation I 2 to the minus li? Yes?
Positive.
It's positive, right? So this is less than or equal to 1. So 1 divided by 2 to the minus li is greater than or equal to 1. So this is greater than or equal to log 1, which is 0. Right? So we started out with the difference between the expected length of any prefix-free code minus the entropy of the source, and we just showed that this is always greater than or equal to 0. Right? So therefore, for every prefix-free code, the expected length must be greater than or equal to the entropy. All right. Any questions so far? Okay. So when do you have? So this is an inequality. When is it an equality? So when do you have equality in the log sum inequality?
When the graph's inequality that satisfies the equality, it's equal to.
Exactly. So when Kraft's inequality is an equality, then it would be an exact equality. But so that certainly if this is equal, then it is exactly equal to 0. But if you go back to the log sum inequality, when is this an equality? Do you remember? Equality in so you have summation over ai log ai by bi, and you know that this is greater than or equal to summation ai log summation ai by summation bi When is this an equality?
AI equal to BI.
Right, so AI equal to BI, or well, in general, log sum inequality, it is when they are proportional to each other. So AI equal to some constant times BI for all I. In this case, anyway, we want these to sum to 1. So particularly when there are probability distributions and like probability distributions, essentially the only option is AI equal to BI. So therefore, we have equality. The expected length is going to be equal to the entropy when Pi is equal to 2 to the minus Li. All right. So can this happen for all distributions? Can you choose Li such that Pi is equal to 2 to the minus Li?
No.
No. So what kind of distributions? So what kind of distributions can you get equality?
Lengths are powers of 2.
Exactly. So, well, lengths are powers of 2. So the probability should also be integer powers of 2, integer powers of a half. Right. So equality, that is expected length, the minimum expected length may be equal to the entropy only if each Pi is some 2 to the minus integer power. The set of natural numbers. Right. So if the probabilities are not 2 to the minus 2 to the negative of an integer, then this inequality is strict. So the expected length will strictly be larger than h of x. So such distributions, Pi equal to 2 to the minus ki for all I, ki being a natural number. So such distributions are called dyadic. Okay, so for dyadic, it may be possible to get an expected length equal to the entropy if Px is non-dyadic. Then the expected length, the minimum expected length, is always going to be strictly larger than entropy. All right. So now let's revisit the Shannon code. So in the Shannon code, what did we do? We set Li to be equal to ceil of log 1 over Pi. Right. Now, if the source is dyadic, if Px is dyadic, then what can you say about the expected length of the Shannon code?
Entropy.
It's going to be equal to the entropy, right? So if Px is dyadic, then log 1 over Pi is always going to be a positive integer, and the ceil of an integer is equal to itself. So for if Px is dyadic, then Li is exactly equal to log 1 over Pi, and the expected length is going to be exactly equal to the entropy. So if your source is dyadic, then the Shannon code is optimal. It gives you the best possible expected length. It is impossible to do better than the Shannon code in terms of the expected length if the source is dyadic. If it is non-dyadic, that's not the case. The Shannon code may be suboptimal, as we just saw an example. Right? We saw an example where the Shannon code is not optimal. It's possible to design a better code than the Shannon code. All right. Any questions so far? Okay. Now, so now if we are given individual symbols coming from some particular probability distribution, we know how to design a variable length code, we know how to encode them, and we know how to decode them. Now, let us say that of course, I mean, in practice, you don't have small symbols. The file consists of a sequence of symbols. Okay, so you have x1, x2, up to xn. Now, there are different approaches you can follow, right? You design, so let's assume that each xi is distributed according to px. We could assume that the xn consists of IID components, or it could have some particular joint distribution. Maybe we'll assume that this is stationary and so on, right? But suppose that each xi is distributed according to the same px. So it's stationary. It may or may not be IID. It could have memory. It doesn't matter. But now I could encode the sequence by encoding individual symbols, right? So I concatenate the encodings of x1, of x2, and so on. Right? So this is one approach. But then, now if I didn't care about computational complexity and so on, I could also encode groups of symbols. Right? I design a code for the entire sequence itself. So xn is distributed according to pxn. So I design maybe a Shannon code with according to this particular probability distribution. So approach number one is you design a Shannon code for xn, for x, for each xi separately. So that is corresponding to the distribution px, and then do symbol-wise encoding. By that I mean that we just concatenate the encodings of the individual symbols. So this has some advantages. Since we have to design a code for px only, and this alphabet is something which is small, and typically n is very large. So the computational complexity of designing the Shannon code itself is not too large. So it is the complexity. So the complexity of designing the code design, and encoding and decoding is small. Right? The complexity of code design just is whatever. It's some function of the alphabet size. Right? So since the alphabet size is constant, maybe 256 or something of that sort, 256 or 512, whatever. If you're assuming ASCII, 8-bit ASCII is going to be 256. So it's not too large. And encoding and decoding, well, you have to encode each symbol individually. So the complexity of encoding grows just as order n, it grows linearly with n. You just have to encode each symbol one at a time. And the complexity of decoding is also order n, because complexity of encoding or decoding a single symbol is some constant, depends on the alphabet size, of course, but then there are n symbols, so the complexity is just order n, both for encoding and decoding. So that's fairly simple. That's good. But now, what about the expected length? Right. So we want to understand what is the expected length for the entire sequence. Correct. So the expected length for the entire sequence, what is this going to be equal to? In terms of the expected length of the code, which is L of x. So we know that expectation of L of x or L of xi is going to be less than or equal to, is always greater than or equal to h of xi and less than or equal to h of xi plus 1, right, for any Shannon code. But what can you say about the expected length of the sequence xn?
N times that.
Sure, it's going to be n times the expected length, or so if you want to do it stepwise, so it's going to be the total length is, of course, the length of the individual symbols. There are n symbols. So L of xn, the total length of this, the total compressed length for the sequence is the sum of the compressed lengths of each symbol, because you're just concatenating the compressed symbols together. And this is just summation I equal to 1 to n expectation of L of xi. Now we know that expectation L of xi is greater than or equal to h of x and less than or equal to h of x plus 1. So the expected L of xn is going to be greater than or equal to summation I equal to 1 to n h of xi, but less than or equal to summation I equal to 1 to n of h of xi plus 1. Right? So if this is stationary, then this is n times h of x and the right hand side is n times h of x plus n. Correct. So there's a gap. So if you take a very large file size, then of course maybe it's close to n times the entropy, but in the worst case it can be n times the entropy plus n bits, right? Which could be very bad, right? So it's n bits away, and this is particularly bad if the Shannon code will perform particularly badly if the entropy itself is small, right? If h of x is small, then h of x plus 1 could be much larger than h of x itself. So that can prove to be very costly. Okay. So as an example, you can perhaps, I'm not sure if this is a good example, but let us assume that there are three symbols. One symbol with probability 0.99, the second symbol probability 0.005, and the third one with probability 0.005. So what are the lengths going to be? That is CL of log 1 over pi.
188.
Sorry, what is it?
188.
1, 8, and 8. Okay, right. So if these probabilities are very, very small, then these are going to be very, very large, right? And that can prove to be very, very costly. Of course, this is not an optimal code. It's you can always design a much better code, right? In fact, you can choose these to be, I think, 1, 2, 2. The best code would probably do this, right? But then that proves it's only to emphasize the point that the Shannon code can perform very badly, and this gap can prove to be expensive if n is very large, if the file size is very large. So then you may say, okay, fine, instead of encoding individual symbols, let me try to design a code for the entire block. All right. So the second approach is
Sir,
yes.
what have you written at 122? I didn't read it.
Oh, okay. So this is log 1 over p, right? So this would be the code word lengths assigned by the Shannon code. Correct? But at least for this particular source, you can do better. You can assign these code word lengths, right? This would be a better choice of code word lengths, right?
Okay.
That's all. Okay. So we did symbol-wise encoding, but now assuming that we don't care about computational complexity, we could also design the Shannon code for the source itself. If you look at the joint distribution pxn and basically design the Shannon code for the entire source xn. So in this case, what is the expected length going to be? L of xn, it is going to be, I'm not doing symbol-wise encoding anymore. I'm looking at the entire sequence as my alphabet. So my new alphabet is xn itself. It's a huge alphabet and it has a huge number of probabilities. It's going to be very complicated to design the Shannon code, but nevertheless, it's possible if I invest a huge amount of computation into it. And the best expected length I can hope for is h of xn plus 1, but greater than or equal to h of xn. Right? So the expected length I can get is between h of xn and h of xn plus 1. So this is if I do block-wise encoding. If I design a Shannon code for the entire sequence. So in this case, the encoding of xn is not obtained by encoding the individual symbols. Right? So the expected length has come down from n times h of x plus n. If it's an IID source, maybe h of xn plus n to h of xn plus 1 bit. Right? So in terms of expected length, this is better. And in terms of the rate, which is expected xn by n, so for large enough n, as n tends to infinity, what does this achieve? Yes. what does this achieve? What is the asymptotic rate?
Entropy.
Right, so it's the entropy for IID sequences. This is h of x if it is IID, or it's equal to the entropy rate for an arbitrary sequence. So defined in the following manner: h of xn by n, the entropy rate which may be smaller than h of x if the sequence, if the source is stationary but not IID. For example, if it's a Markov chain, it's a stationary Markov chain, then this entropy rate could be smaller than the entropies of the individual symbols. All right. So, but of course, there's a price to pay. Now, the complexity of designing the code of encoding and decoding is not small anymore. In this case, how does the complexity scale with n? If I sort of design the Shannon code for xn itself, then complexity of whatever, of encoding, decoding, and code design
So code design will be the entire sequence.
yeah, the entire sequence. So you basically look at all possible p of xn's, so the probability of all possible sequences, and then compute log 1 over p of xn for each xn. You'll get a set of lengths, and then design a Shannon, basically the Shannon code using the tree for that. All right. So roughly, how would the complexity scale as a function of n? Is it going to be linear, constant, exponential, polynomial?
Exponential in 2 power n.
Yeah, so it's going to be exponential. And why do you say it is exponential in 2 power n?
Like the sequences are bits, so each it will be in some terms of bits. So every character in it will have 2 chances of encoding. So some power of 2.
So why do you say so? Okay, so let's go back. Fine. So firstly, it's at least exponential in n. That's fine. So the claim now is that it's exponential in 2 power n, or whatever. It's super exponential in n. In n, and so let's see how many. Let's look at each step of the code design process. You have to compute log 1 over p of xn for all possible xn's. Let's assume that each computation takes constant time. So this would take overall how much time? Exponentially in n, right? Is this okay?
Yes, sir.
Okay. So now the main computation comes in designing the code. Designing the code words. Right? So what is the complexity of designing the code words? What do you need to do? You need to first construct the code tree, right? And what is the size of the code tree going to be? How does it grow with n?
Exponential again.
It's exponential in
2 power n.
exactly whatever. Yeah. So it's exponential in the into power n, or it's exp of n. So it is 2 to the order n. Right? So it is super exponential in n. All right. So the code design process is super exponential in n. What about the encoding and decoding process? So forget about the storage space required to sort of store the code tree. We'll assume that that comes for free. Essentially, what you need to do is sort of search.
Sir, sorry to interrupt. I'm getting a little confused between the two methods when you're saying symbol-wise encoding and the entire sequence.
Okay.
Symbol-wise, like every symbol, I'm mapping it to the code.
Okay. So let's take a
entire sequence also. We will take like the mapping will be symbol-wise only, no sir. That
Okay. So let's take a very simple example. Let us assume that yeah, what did we had an example here, right? That we already had. Fine. So this example, right? So let's assume that this is our source. Okay. So with probabilities, so this is the code that we designed. If we did symbol-wise encoding, then the encoding of say A, C, D would be what?
encoding of A.
Yep. So
Then
that is 1 0 1 1 0 0, and then D is 1 1 0 1. Correct?
yes, sir.
Fine. So now suppose let's take something smaller. So encoding of AC would be 1 0 1 1 0 0. Right? Now, if I did blockwise encoding, my new alphabet is the set of all possible pairs, which is AA, AB, AC, AD, BA, BB, BC, BD, and so on. So I compute the probabilities of each of these, right? And try to construct a code for each of these, right? Find the lengths and then design a new tree. And the encoding there could be different from what I have over here, right?
Yes, sir.
Right. So take something very simple. Take two symbols, right? So X is AB. The probabilities are, let us say, 0.8 and 0.2. Okay. So the code would be, I don't know, what is log 1 over 0.2? I think we've already calculated here, right? I think probably 3. 1 over 0.2 seal. What is this equal to?
So 2.32. So C 3.
Fine. So it's going to be 3 So the code words are going to be, say, 0 and 100. So this is going to be the code. Now, if I look at it block-wise, maybe, so therefore basically the encoding of, say, AB is going to be 10100. Now, if I do it symbol-wise, I'm going to look at all possible pairs: AA, AB, BA, and BB. The probabilities now are 0.8 square, which is 0.64, AB, which is 0.16, BA is also 0.16, and BB is going to be 0.04. So the lengths now are going to be 1. What is log 1 over 0.16? Something. So let's say that it is, assume that it is, hopefully is going to be 3, and this might be, I don't know, 4 or 5 maybe. So if I do block-wise encoding, if I design a code for this particular, for blocks of 2 symbols, then my code is going to look different. So in this case, AA is encoded as just 0, whereas if I do symbol-wise encoding, AA would be encoded to 00. 00. It's just the concatenation of the two, whereas in this case, AA gets a separate code word for itself. Just 0. Right?
Yes, sir.
Okay. So now, so we'll end here, but for just one last point. So therefore, if I do block-wise encoding, what is going to be the complexity of encoding and decoding?
So there, we're considering the length n, no? So here,
So here, remember, the length is n. It's as though you're encoding a single symbol and decoding a single symbol over an alphabet of size of x raised to the n. Right? You're treating this as a super symbol and designing a code and then encoding and then decoding.
it'll be n only.
Why do you say it is going to be n?
So this xn will contain different combinations of the, I mean, like A, B, C kind of thing.
Correct.
So now if I have to encode each of them, then again the complexity is n.
No, I'm not encoding each of them, right? So I'm
Each
encoding
means
them as
each means each combination.
yes. It's not going to be O of 1. Anyway, think about it. Think about how you would sort of encode and decode an arbitrary Shannon code, right? So you know what the complexity of designing the code is. Now, if I give you an arbitrary Shannon code over an alphabet, say script X, then what is the complexity of encoding and decoding a single symbol in terms of the size of x? Encoding and decoding complexity as a function of the size of x.
So, sir, n is the size of x and not the sequence length.
No, so n is the length of the sequence. The size of the alpha. Okay, so you have a sequence of length n, right? You have a sequence of length n. The length of the sequence is n. I can treat this as a sequence of length n over an alphabet of size, whatever, size of calligraphic of x, maybe m. So it's a sequence of length n with an alphabet of size m. Or I can also, so that is what I do in symbol-wise encoding. Whereas in block-wise encoding, I treat this as a sequence or a single symbol. So single symbol, which is a sequence of length 1, but the alphabet size is now size of x raised to the n, right? So this is what you would do in block-wise encoding. So this is m raised to the n. Whereas this is symbol-wise. You treat it as a sequence of length n over an alphabet of size m, whereas when you're doing block-wise encoding, you treat it as one super symbol of, so it's a sequence of length 1, but the alphabet size is now m raised to the n. Right? So just think about this particular example what we just had. All right. So if you look at pairs of symbols, you can look at them as two different symbols coming from the same alphabet, or I could just club those two together, call them something different. So A1, A2, A3, and A4, where A1 basically is AA, A2 is AB, A3 is BA, and A4 is BB, and the probabilities are 0.64, 0.16, 0.16, and 0.04. So as n increases, if you do blockwise encoding, then the alphabet size, the super alphabet size, it grows exponentially in n. But then if you do symbol-wise encoding, the alphabet size is always the same. It's a constant. All right. Any questions? Okay, so let's stop here. We meet again next week. Sorry, we meet tomorrow. So see you all tomorrow.